Also in the sense of keeping these short, the time domain group ended up with, I'm going to say, two technical configurations. The first, something like an all VLASS sky survey, somewhere in the band 1 to 4 gigahertz, and I don't know that we got into details as to whether 1 to 2 or 2 to 4 gigahertz would be preferred. Sort of arc-second-ish resolution, multiple passes would be preferred. The science case coming out of a technical configuration like that, I won't read it to you other than there's a whole slew of time domain work. I'll highlight one of them, is the reference sky for future work. This is in the sense of the way that the NVSS and FIRST have been important for subsequent work. The other technical configuration is, this question came up sort of late and we don't have an answer to it. But can the wide arc configuration, I think this would be probably most applicable at the 1 to 2 gigahertz band, to use a slightly reduced bandwidth for the main survey? Because after all, even though we say 1 to 2 gigahertz, because of RFI, you really only get probably 700 megahertz of usable bandwidth. Thus, could you trim that down to 500 megahertz and then configure the correlator so that there's a separate 256 megahertz band doing fast dump at something like 100 milliseconds? The localization of what are probably or potentially or could be extragalactic fast radio bursts, and there would also be synergy with VLASS.
I should try to do that,
yeah. Yeah, I did ask our staff about it. They said, maybe.
Yeah. That's consistent, that's good.
So, thoughts?
Next.
Comments? Oh, you have more slides? You have more slides?
No.
Okay. So, does anybody want to interact on this topic?
So I'm going to ask a very stupid and naive question. What time scale of time domain variability are we talking about? I mean, we heard nanoseconds to years.
Yes.
Mentioned. So
this one is the 100 milliseconds, you know, if you could push that one faster, that would be better. This one is down at the 100 millisecond or faster.
Right.
This one, in terms of the multiple passes, I would invite comments from other people at the table. My opinion would be we don't have a really strong science case for what the defined epoch would be, but something on the month to year time scale. I mean, I think feasibly you probably couldn't do it faster than a few months, right? Just cover the sky and then go back and do it again. That's going to take several months.
The larger the better, basically. If you're constrained to a small number of epochs, as well separated as possible, because as you go to longer time scales, the number of trends that you detect will increase and it'll flatten out. As you go to longer time baselines, it will stay flat. So if you're limited by the number of epochs you have, I don't think unless other science cases define it, I don't think we'll be doing like 10 passes to constrain the time scales. It may be that other science cases dictate that to be the case. So, but if it was just a transience-defined survey, you can try and do as wide as you can and smaller.
But we could, I mean, three epochs that are then co-added later to form the reference sky would probably be acceptable. Sorry.
So I think the calculations I did show that for I think it was 256 megahertz band at 100 milliseconds, you have to survey for like 5,000 hours to find one aspect burst. So if you can go faster than that, that would be way better.
Well, I mean, I think you heard, we don't know yet if the correlator could even be configured in this, so.
Yeah, I guess the issue is you have to split it.
Yeah.
And I think it's mostly the back end of the correlator.
Sorry, yeah.
Just to quantify,
Even though
for every n value you move away from a match filter, these are typically duration, milliseconds or less. For every value of n you move away from that, from having a match filter to that burst, your n to the power n to the power 1.5 less optimized. So you instead of having, if you have a factor of 2 in time resolution away corresponds to 3 times, you need 3 times the time. So going from 10 to 100 milliseconds is 10 to the power 1.5 times less optimized, or you need that time, that amount more time to find the same amount of bursts. Like Sarah said, it becomes pointless at a certain point.
Thus, there's a missing less than. So.
And would you want to archive all of those fast dump data or try and do a real-time search with that? Because there's also disk
Just
space
this, yeah.
issues with saving all those data.
It would almost have to be a real-time system, or at least something that searches it and then decimates it.
I mean, in my mind, the first question would be, can you even do something like this? And then the second question is if it's even possible. I know what you mean in terms of the archive requirements. And then you probably have to figure out, can we live with some kind of decimation, or what level of decimation can we live with?
On the new pulsars, in the case of the SKA, I always hear the argument that the only way you can do the pulsar searches and timing and still have a finite size computer is when the SKA is only a kilometer in size, in which case the arc-second resolution and the new pulsars seem to be incompatible.
This is very much in the range of what Sean was describing. You're not doing a periodicity search, you're looking for compact sources, which is part of the reason for going to the arc-second resolution, and then using other filters such as polarization or variability to try to select out what are the extragalactic versus the things you can't identify and you do more intensive work on.
I'm not sure that the resolution of even the A configuration at low frequencies is enough to winnow out enough extragalactic sources.
You're
The
not
median
just,
angular size is only an arc-second or so.
Right.
well, you won't just use that. You will start with that and spectral indices and polarization, but you'll be adding extensive existing multi-wavelength patterns to then winnow it that way.
So on that, so I looked into this with Arish Krastoji for the SKA, because it seemed like a good way of reducing the required the pulsar set for SKA. And I think I came to the same conclusion that Jim just mentioned, that there's too many contaminating sources. Even when you get to cross-matching with optical data, you get to the point where all your sources are unresolved because they're all star-forming things at this resolution. And your optical surveys aren't deep enough over that area to reduce your contaminants.
I think it should be a discussion. Go ahead.
So I think it's a function of how deeply we're growing, because I think your comment and maybe Jim's are based on going down to what, below 10 microjansons?
No, this is for 100 microjansky continuum depth. So,
yeah, okay.
The only thing I'll add is there is an effort undergoing now to actually try to do this with the modern JDOA, because it has been tried in the past, it's been spectacularly unsuccessful. But there's now an effort to do this and show that it works on a pilot field or set of pilot fields.
So Joe, I mean, there are several white papers on this that looked at this in some detail. Do you have a feel, ballpark, what the resource requirements are in terms of raw hours? How big an observatory commitment are we talking about?
We certainly in the discussions over lunch, we did not get into hours, and this, I think, is phrased in the sense of a way of trying to match up with what other groups might be thinking in terms of a all-sky survey.
There's no statement here about depth on front of those.
So, a border 5,000 hours get down to a couple of these box down to about 100 microjansons or so. At S-band, for example, we're talking about on the entire sky.
Good point. At the
So it's a solid year of observing time.
No, yeah, which is compatible with multiple passes.
It's basically equivalent to NVSS. It says 20 multiple epochs, and with the large bandwidth of the EPO.
Okay.